Hey, welcome back to your favorite pre-calculus course. We're going to take a look at rational functions. So rational functions are any function where you've got a polynomial on the top as your numerator over some other polynomial as the denominator. And to find the y-intercept for a rational function, we're still going to let x be 0. To find the x-intercept, we're going to let y be 0. Or in other words, the function to be 0. So let's go ahead and do that initially first. Let's find our intercepts here for this rational function. Notice we've got a polynomial on the top, we've got a polynomial on the bottom. So this is a rational function. To find our x-intercept, we're going to let y be 0. To find our y-intercept, we're going to let x be 0. So let's go ahead and let our y be 0. Now, what makes this true? What makes this true? Well, if our numerator, if this is 0, right? 0 over x plus 2 would be 0, and that would make it true, right? So when we're doing this, all we have to do is take our numerator and set it equal to 0 for a rational function, right? And that would make it true. That would be finding our x-intercept. So let's go ahead and add 12 to both sides. So we've got 2x equaling 12, divide by 2. So we've got x equaling 6. So our x-intercept on this is 6. Now let's find our y-intercept by letting x be 0. So we have 2 times 0 is 0, 0 minus 12 is negative 12, 0 plus 2 is 2. So it looks like our y ends up being negative 6. So this rational function has the point 6, 0, and then 0, negative 6 on it. Now we're going to talk about asymptotes for these rational functions. And this is the behavior as x approaches or y approaches infinity. So there's two types. Okay, first of all, a vertical asymptote, and that's where the function is undefined. So for example, with this function we had, y equals 2x minus 12 over x plus 2, the vertical asymptote is where is this undefined? In other words, we know we can't divide by 0, so we'd have a vertical asymptote wherever x plus 2 equals 0. Let's solve that at x being negative 2. So the function, if I was graphing this thing, would never touch that line x equaling negative 2. X equaling negative 2. And so for a vertical asymptote, the question is, as I approach negative 2, if I plugged in a bunch of points around it, like if you plugged in like negative 1, for example, let's say we plugged in negative 1 just to see where that's at. We got negative 2 minus 12, we got negative 14 over 1, so it's down here, way down here at negative 14. And I could plug some other points in, like that are even closer to an x value of negative 2, like negative 1, negative 1.5, and it's even further down. But as I approach that vertical asymptote, see how it's shooting me way down there, the graph is? Negative 2, I have that point, negative 2, negative 14. Or I'm sorry, negative 1, negative 14. If I plugged in negative 1.5, it's even further down than negative 14, and so on. So a vertical asymptote, what it's going to do with a rational function is as I approach that imaginary red dotted line, it's going to shoot me to negative infinity or to positive infinity, as it would on the other side. Okay, so that's to find a vertical asymptote. The horizontal asymptote depends on the degree. Okay, so here's the formal definition of a rational function. And what I'm looking at is I'm looking at the degree of the top, n, and the degree of the bottom, m. Okay? And so for the function that we had, y equals 2x minus 12 over x plus 2, the degree of the top is 1, the degree of the numerator is 1, the degree of the bottom is 1. So if, look at number 2 right here, if the degree of the numerator is equal to the degree of the denominator, then you take their leading coefficients. So I say, since n equals m, i.e. the degree of the numerator is 1 equaling the degree of the denominator is 1, then the horizontal asymptote is the leading coefficients. Well, the leading coefficient of the top is 2. The leading coefficient of the bottom is 1. So it's y equaling 2 over 1. Y equals 2. So if I was graphing this, let's go back up here. Y equals 2 is this horizontal line right there. So the further out I go, as x gets larger, 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 it's going to get closer and closer and closer to that y value of 2 on that side. Okay. Now, I didn't graph the other side, but if you had plugged in a bunch of points, it's going to look something like this. So notice as I pick values to the left, the further out I go, the closer it gets to that y value of negative 2. Okay. We'll practice a bunch of these. So that's if the degree of the top is equal to the degree of the bottom. Now there are other scenarios. Scenario 1 is if the degree of the top is less than the bottom, so like for example, y equals x minus 2 over x 2x to the third minus 2x plus 1. See how the degree of the top is 1, the degree of the bottom is 3, the degree of the top is less than the bottom? Then automatically that one would have a y equaling 0 horizontal asymptote because the degree of the numerator is less than the degree of the denominator. Okay, and we'll talk about more why that is as well for these scenarios 1, 2, and 3. Let's look at the third scenario for a horizontal asymptote. The third scenario for a horizontal asymptote is if the degree of the numerator is larger. So like let's say you have 2x cubed minus 7x plus 4 over, let's say, x squared plus 1. See how the degree of the numerator is larger than the degree of the denominator? That means there is no horizontal asymptote. And if it's only a difference of 1, so the degree of the top is only 1 more than the bottom, right? Like in this case, a cubed over an x squared. Then you will have what's called an oblique or slant asymptote. And we're going to do long division to do that. We'll do that later. Okay? So this one we already did this. We found our vertical asymptote. Where's this thing? Undefined. Subtract 2 at negative 2. We did the horizontal asymptote as well. The degree of the top is 1, degree of the bottom is 1. If they're the same, I take their leading coefficients. So y equals 2 over 1, y equals 2, right? So that was that one. Let's go on and do some more here. Let's identify domain range, intercepts, if any, horizontal asymptotes, vertical asymptotes, oblique asymptotes, if any. Okay? So if I'm looking at this, initially I'm looking at the domain and range. Let's talk about the domain for a minute. It is not continuous. I can't draw this without lifting my pencil, right? I'm going to have some breaks here. So where are the breaks at? Well, hopefully you notice these red vertical asymptotes. This is where I have breaks in it, right, in my domain. So my domain is coming from negative infinity until that first break, that first vertical asymptote, and it's not defined there. It stops at -2. I never touch an x value of -2. And then if you notice, in between, I'm all defined in blue there, right? In between -2 and it looks like 1. But I have another break at an x value of 1. I have another vertical asymptote at an x value of 1. But then I take off again after 1. See how I take off again after 1? So there, that would be my domain on this one. And my range kind of hard to see, but hopefully you notice this y equaling 0. That's a horizontal asymptote right there. And the question is, I'm coming from negative infinity. Do I ever cross a horizontal asymptote? Oftentimes not, but if you notice, this one actually does hit right there in black. It actually does cross this horizontal asymptote. So you're not going to cross a vertical asymptote, but a horizontal asymptote sometimes will cross. This one does. This one does. Okay. So it does hit a y value of 0, and notice it still keeps going up. So this range actually has no restrictions because it actually hits 0 as well. Now that's not always the case. Like if maybe here's another one. Maybe I have a graph that does this and then this. And it has that horizontal asymptote. This range would be from negative infinity up to 1 and then never crosses the 1. It keeps going after 1. Okay. So that's a little different range. On that. All right, let me erase it. We've done part A, the domain and range. Let's look about, is there any x-intercepts? Any x-intercept? Does it cross the x-axis? Yes, we noticed that did hit at the origin. So that's not only an x-intercept, that's our y-intercept as well. And there's no other intercepts here that I see, right? Again, let me draw this horizontal asymptote. Notice this blue line. As I go out, I'm getting really close to a y value of 0, but I never quite touch it. As further out I get, the closer I get to a y value of 0. But never quite touch it. I only touch it right there in the middle on this one. That y value of 0. Let's look at horizontal asymptotes. What's our horizontal asymptote? That's that horizontal line, y equals 0. What's our vertical asymptotes? Our vertical asymptotes would be x equaling -2 in red and x equaling 1. X equaling -2 and x equaling 1. Is there any oblique asymptotes? There are no slant asymptotes shown here. All right, let's take a look at this next one here. We're going to find the intercepts and asymptotes, state the domain. If I was doing this, I would go ahead and write this as -x² plus 1. Write that in standard form first. And then I would double check and make sure nothing cancels. So let me take a negative out of this. And let's go ahead and factor that. We got difference of squares here on the bottom. Looks like I have x minus 2, x minus 3. Okay, nothing cancels. So it's a simplified form. And frankly, that'll help us to find our x-intercept. Because if we're finding an x-intercept, we're letting y be 0. And if this is true, then anytime my numerator is 0, that will be a true statement. So I can just forget about this denominator. Say, well, let me set each of these factors equal to 0. So I got 1 and -1 are my x-intercepts. Now I know we're not graphing, but we could go ahead and throw those on. 1 go ahead and find our y-intercept now by letting x be 0. So it looks like we get y equaling 1/6. When x is 0, y is 1/6 right there. Let's find our vertical asymptote. And I'm going to think about it right here in factor form. My vertical asymptote, where's this thing undefined? Well, if x minus 2 equals 0, I have a problem. Or if x minus 3 equals 0, I have a problem. So at 2 and at 3, x equaling 2, I have a vertical asymptote, as well as x equaling 3, I have a vertical asymptote. With my horizontal asymptote, I want to look at this before I factor this so I can see what the degree is. Notice that the degree of the top is 2, degree of the bottom is 2. They're the same. Well, if they're the same, so number one, n equals m, right? Here, the degree of the top is equal to the bottom. Then I take my leading coefficients, so -1 over +1. So y equals -1 would be my horizontal asymptote there in green. And then my domain will be all reals except for where it hits my vertical asymptote. I won't hit the vertical asymptote. So everything except for the 2 and the 3. So I'm coming from -infinity up until 2, and then between 2 and 3 is fine, and then after 3 is fine. So again, notice I have the interruptions at those vertical asymptotes for this rational function. Or if I'm doing this one, this would be a great problem to pause and make a u-try problem, but I would go ahead and put this in order. Notice the bottom, I should have that 4x cubed first, then the 2x squared. Let me just double check. Let me go ahead and factor. Make sure nothing factors here. It's like on the bottom here I have a 2x squared that could factor. That would leave me with a 2x plus 1. Okay. And so we could simplify this. Notice that one of these x's would cancel, and one with the bottom. And we'll talk about what that does graphically, but graphically that's going to mean we have a hole there. That's equaling 0. But this will simplify to the function x minus 3 over 2x times 2x plus 1. If you have a function that cancels, what you'll have on the graph is a hole right there. You'll have a hole at whatever that factor is equaling 0. Okay, just FYI, you'll have a hole there. Okay, so like maybe the graph does this, but right there at that, when an x value of 0, you're going to have a little hole. Yeah, there won't be a vertical asymptote there. Okay. Now let's do the rest of this. Again, there's no graph required on this. To find an x-intercept, let y be 0. If this is true, then x minus 3 equals 0. Right? So at x equals 3, we have an x-intercept. So if I was graphing it, I would have that x equaling 3. Y-intercept, let's let 0 be in for x. A simplified form. Well, notice I have -3, but I got 2 times 0. I got 0 times 0 plus 1. I can't divide by 0, so there's no y-intercept. No y-intercept on this thing. Okay. Do I have a vertical asymptote? Yes, I do. I'm going to take a look at where is this thing undefined. Well, if 2x equals 0, x equals 0. If 2x plus 1 equals 0, subtract 1, divide by 2, divide by 2. So x equaling -1/2. So I have a vertical asymptote actually at x equaling 0. And this one also has a vertical asymptote at x equaling -1/2. All right, let's look at this horizontal asymptote here. So I'm looking at the original function. My original function in standard form, the degree of the top is 2. The degree of the bottom is 3. If n is less than m, right, 2 is less than 3, the degree of the top is less than the bottom, then automatically y equals 0 is my horizontal asymptote. Okay? And now I notice I mentioned that we have a hole at x equaling 0 on this because we had the factors cancel. But because we have a vertical asymptote, I don't have to worry about that anyways. It's never defined there at x equaling 0. Okay? Again, we're not getting into the graphs on these, but just so you have an idea when we get into those. Let's look at another one here. Again, another good time to pause the video if you'd like to and try the problem here. So if you're looking at this, do we have any vertical asymptotes? Well, we'll have a vertical asymptote as long as nothing cancels. Let's go ahead and see if anything cancels. If I was to factor the top here, it looks like I'd have, let's see. Yeah, that doesn't factor. Okay, so it doesn't factor. So we can just say, well, we've got a vertical asymptote. Where's this thing undefined? At -2. At -2. Horizontal asymptote. Well, the degree of the top is 2. The degree of the bottom is 1. If the degree of the top is greater than the bottom, right? The degree of the top is 2, the degree of the bottom was 1, then there's no horizontal asymptote by our rules. Now, if the degree of the top is only 1 more than the bottom, which it is, right? The degree of the top is 2, it's only 1 more than the bottom. There's only a difference of 1 there. Then I will have an oblique asymptote. So yes, we will have an oblique asymptote. So how do you find the oblique asymptote? Well, what you do is you take this 3x squared plus 10x plus 6, you go ahead and you divide it by that x plus 2, and you go ahead and use your long division. Let's go ahead and do that. Don't forget to change your signs. Change your signs there. So it looks like I have a remainder of 2. So this y equals 3x squared plus 10x plus 6 all over x plus 2 can be simplified as 3x plus 4 plus the remainder over the divisor. Now notice as x shoots to infinity, this part's going to go to 0, right? As x gets really large, as this goes to infinity, it's like -2 over a huge, huge number. Okay, so this stuff is going to go to 0 because the denominator becomes hugely large, very huge, right? Increase in magnitude there. And so you're left with right here, oops, that right there is your oblique asymptote. So it's that quotient that you get, the line y equals 3x plus 4. Well, if I was graphing y equals 3x plus 4, I've got a y-intercept of 4 and a slope of up 3, right 1, up 3, right 1, and so on. And so this red line is my oblique asymptote. So as x gets increasingly large, the function will approach that slanted line y equals 3x plus 4. All right, let's take a look and get into some graphing with these transformations. Now, if you're graphing 1 over x, that's the one on the left. Notice this has a vertical asymptote at x equaling 0 right down the middle, right? Degree of the top is 0, degree of the bottom is 1. So it's going to have a horizontal asymptote y equals 0. Same vertical and horizontal asymptotes on y equaling 1 over x squared, except notice that's our graph on y equaling x squared, right? All right, let's use those graphs to do some transformations. Y equals 1 over x minus 3. Well, this is a lot like the one on the left. Y equals 1 over x. The one on the left, let's do it in blue here. Except we've moved it right, I can't spell, 3. Except we've moved it right 3, right? And if you're not sure, then go ahead and just graph what's your vertical asymptote. Well, where's this thing undefined at x equaling 3? I would put x equaling 3 on there. I would also do my horizontal asymptote. 1 over x minus 3. The degree of the top is 0. The degree of the bottom is 1. If n is less than m, then it's automatically y equals 0. And I would just graph a bunch of points if I was graphing y equals 1 over x minus 3. You can't graph it at 3 because that's your vertical asymptote, but you can throw on some points around it if you'd like. If you plug in 4, y equals 1 over 4 minus 3, 1 over 1, right? So again, that's your vertical asymptote. That'd be negative 1, 1 half, negative a half, and so on. And so it's going to look like that function just moved right 3. Sorry, if n is less than m, y equals 1. I just noticed my horizontal asymptote was pointed out to me. Thank you. That is y equals 0. I did graph that y equals 0. We've got negative 1 over x squared plus 6x plus 9. I would go ahead and factor this first. Notice this will factor into x plus 3 times another x plus 3. So I would be thinking, I'm like, well, that's a lot like this 1 over x squared graph. If you remember, the 1 over x squared looks like that. Except for the negative out front would reflect it about the x-axis, number 1. So that would look like this. And then it would go left 3. Left 3. Not my greatest graph in the world, but now let's go ahead and do that. If I didn't do it with transformations. So number 1, where's my vertical asymptote? Well, where's this thing undefined? At x being negative 3. So I would put my vertical asymptote, x cannot be negative 3. Secondly, where's my horizontal asymptote? Well, the degree of the top is 0, x to the 0, don't write that in. The degree of the bottom is 2. If n is less than m, then there's no horizontal. I'm sorry, if n is less than m, sorry about that, y equals 0 is our horizontal asymptote. There it is. And then again, I would just graph a bunch of points to get a feel for this. I would graph them around my vertical asymptote. So I'd pick points to the left, points to the right, and I would plug them in one by one into my function. And then I'd graph it. It should look the same as if you did it with transformations. All right, if I was doing this with transformations, I would think about this as 1 minus 1 over x. In other words, negative 1 over x up 1. So I'm thinking about, here's y equals 1 over x is like this. The negative would, number 1, reflect it about the x-axis. So now it would be like that. The plus 1 would just move the whole thing up 1, vertical shift up 1. So everything's now up 1 in green. So that's kind of what I'm expecting to see if you're doing this with transformations is that green one right there. Okay, now let's go ahead and go through this formally as if we did not do it with transformations. So the vertical asymptote, where's this thing undefined? X equaling 0. So if I'm plugging points in, I'm doing it around 0. Alright, this is a vertical asymptote, but I can plug in points around that. As far as my horizontal asymptote, degree of the top is 1, degree of the bottom is 1. If n equals m, if the degrees are the same, then I go ahead and take the leading coefficient. So y equals 1 over 1. So y equals 1. My vertical asymptote was x equaling 0. And then I'm plugging a bunch of points in. Let's plug in like 1. 1 would be 0. 2 minus 1 is 1/2. Negative 2 over negative. So plug in negative 1. Yeah, negative 2 over negative 2. Negative 2 is negative 3 over negative 3/2. And we can graph as we expected with our transformations. So our domain would be everything except that vertical asymptote. It's not going to hit that 0. Our range, it doesn't look like it crosses that. It's not hitting that horizontal asymptote of y equals 1. So everything up until the green, and then it takes off again. So negative infinity up until the 1 y value, and then it takes off again. And this one, by the way, has no oblique asymptote, right? That's not applicable here. Let's try this one here. We've got x plus 1 over x squared minus 9. X plus 1. I'm going to factor the bottom. X minus 3, x plus 3. Let's find our x-intercept by letting y be 0. So this will be true anytime the numerator is 0. The numerator is 0 will be 0 over whatever. So x equaling negative 1 is our x-intercept. So we hit right there. Our y-intercept, we're going to let x be 0. So we have 0, comma, negative 1/9 there. Now, our vertical asymptote, where's this thing undefined? Well, anywhere where the denominator is equal to 0. So we got x minus 3 is a factor of the denominator. X plus 3 is a factor of the denominator. So 3 and negative 3. I'm going to put those vertical asymptotes on there. 3 and negative 3. My horizontal asymptote, the degree of the numerator, is 1. Degree of the denominator is 2. So my horizontal asymptote of n is less than m, right? 1 is less than 2. It's automatically y equals 0, because as x gets increasingly large, that denominator will become really big, so it's going to approach a y value of 0. Now notice that black point. I did cross. All right, I did cross that horizontal asymptote right there. All right, we did have the point negative 1, 0. Now, after you have this information here, I would go ahead and plot a few points around your vertical asymptotes. You can't have negative 3 or 3. Those are vertical asymptotes. We already know negative 1 is 0. We know when we plugged in 0, we got 1/9. So maybe 1, 2, 3 is a vertical asymptote. And here's a bunch of points we could throw in. Right, and we're throwing them in one by one. And soon enough, you're going to kind of see. This is not the greatest graph, but I want to plug some points in. Let me throw in like 4 for a second. Let me just double check where 4 is. 4 plus 1 over 4 squared minus 9. I got 5/7. So 4 and I'm up 5/7. And again, plot a bunch of points on that. Same thing over here. Plot a bunch of points. You kind of get the feel for that. That'll help you get some accuracy. Well, let's take a look at this next one. Notice it's not in factored form. I'm going to go ahead and factor out a 2x initially. And it looks like the denominator will factor into plus 5 and minus 3. Looks like no factors cancel. Let's go ahead and find our x-intercept by letting y be 0. So if the numerator is 0, we'll have an x-intercept. Divide by 2, divide by 2, I get 0 and negative 2. So 0, 0, negative 2, 0. So I have 2 x-intercepts there. Now let's go ahead and find our y-intercept by letting x be 0. And I got 0 plus 0, I got 0 on the top over negative 15 on the bottom. So it looks like this is 0, right? So we have when x is 0, y is 0. We already knew that. We already had that origin point, right, as the x-intercept as well. Now our vertical asymptote. Let's go ahead and, where's this thing undefined? Well, whenever x plus 5 equals 0 from our denominator, factor of our denominator, or x minus 3 equals 0. So subtract 5 both sides, add 3 both sides, so x equals negative 5. X equals negative 5, and x equals 3. Put my vertical asymptote on there. Now when I'm thinking about my horizontal asymptote, go back to the standard form here, and I say, well, my horizontal asymptote looks like the degree of the top is the same as the bottom. If they're the same, then we're going to go ahead and take the leading coefficients, 2 over 1. So y equals 2, 2 over 1 would be our horizontal asymptote here. So it now brings us to the tedious part of plugging a bunch of points in. So like negative 5 is one of my vertical asymptotes. It'd be nice to plug in a couple points to the left of that. Plug in points to the right of that vertical asymptote, like negative 4, negative 3. Negative 2, we know it hits 0. Negative 1, 0 also hits 0, we know that. And then 1, 2, 3 was our vertical asymptote, so it'd kind of be nice to throw in like a 4, maybe a 5. And let's throw them in between those two x-intercepts, like negative 1. Let's throw negative 1 in. So I got 2 times negative 1 squared plus 4 times negative 1. Whoops. All over negative 1 squared plus 2 times negative 1 minus 15. I got 2 minus 4, I got negative 2 over 1 minus 2 minus 15. So we got an 8th. So I got negative 1 is up an 1/8 of the way. 1/8 of the way right there. And we could throw in negative 3. We throw in a few of these, like negative 3 would be about negative 1, I think. Anyways, it'd be nice to throw in a bunch. I won't take all your time here, but you're going to kind of see this pattern over here. I would throw in some maybe to the right of 3, like 4. So ends up being 48 over 9. Which is 5 and, what is that, 5 and a third? 5 and a third. So 4, 1, 2, 3, 4, 5 and a third, about right there. Anyways, I could throw in some more points. You can kind of see that over here. I'd throw in some other points, so you're going to kind of see that over there as well. It'd be nice to throw in like -6, -7, and so on. All right, let's take a look at this next one here. I'm going to go ahead and factor this. We've got difference of squares on the bottom here. Let's find our x-intercept by letting y be 0. So that will mean x equaling 0 is our x-intercept. So 0, 0 is our origin point. Let's find our y-intercept by letting x be 0. So let x be 0, I got 0. Right, we already know we have that origin point. So there's our x-intercept and our y-intercept. Now let's find our vertical asymptote by setting those factors at the bottom. Where is this thing undefined? Where does x minus 2 equal 0? At x equaling 2. Where's the other vertical asymptote? X equals -2. So let's put those x equaling 2 on, x equaling -2 on. Our horizontal asymptote, let's go back to this in standard form here. Degree of the top is 1, degree of the bottom is 2. If the degree of the top is less than the bottom, this is automatically y equaling 0. Now notice we actually hit this, right? We hit it at the origin, so it does cross this horizontal asymptote right there at that origin. And at this point, I'm just plugging in a bunch of points again. So -2 would be nice to throw in a couple to the left and right of those vertical asymptotes, right? And kind of tedious, but let's go ahead and we already got 0, 0. We can throw in a few. I'll pause the video and throw in a few points here. You can see I plugged in a bunch of points here. -1, I'm up a third. 1, I'm down -1/3. And you could plug in, like, if you needed to, -1.5 or whatever, but it's going to shoot this thing up. And then the closer I get to 2 over here, it's going to shoot this thing down. Let me throw in 3 gave me 3/5, 4 gave me 1/3. I could plot some more points if you'd like to, but you're going to see that over there. Over here, I got -3, -3/5, and 4, -1/3. And I could plot some more points if I needed to with my scientific calculator. And that's kind of what you'll see with this function. Notice this next one here, also not in factor form. We'll go ahead and factor it. Difference of squares in our numerator here. So what's our x-intercept? If I let y be 0, I got 2 and -2 if y is 0. And -2. If I let x be 0, I can't divide by 0, right? So that's a no-go because we have a vertical asymptote there, right? Where is denominator? Where's this thing undefined? Right down the middle. That's why we have no x value of 0, right? As far as the rules, degree of the top is 2, degree of the bottom is 1. If n is greater than m, 2 is greater than 1, there's no horizontal asymptote. And if it's only 1 degree bigger, then what we have is we have a slant asymptote because the degree is only a difference of 1. So we have a slant or oblique asymptote. So let's go ahead and find that. We have to do the long division, right? This is x squared minus 4 over x. So I'm going to go ahead and x squared plus 0x minus 4 over x plus 0. Go ahead and do our long division here. Bring down the -4. So That'd be a plus 0. 0x plus 0. Change those signs. Of course, that makes a difference. We get a negative 4 there. So this ends up being y equals x plus remainder over divisor. Negative 4 over x. Well, this is going to go to 0 as x goes to infinity. So this right here, that's your oblique or slant asymptote, y equaling x. So if I graph y equaling x, has a y-intercept of 0, up 1 over 1, this green line would be y equaling x. And then at this point, I just want to plot a bunch of points around my vertical asymptote, x being 0. As you think you need. So we've got y equals x squared minus 4 over x. Let's throw 1 in. I got 1 squared minus 4 over 1. I got negative 3. If I plug 2 in, that was 0. Negative 2 was also 0. So I got 1, negative 3, 2, 0. Let's plug 3 in. I got 5/3. So 3. I got 1 2/3. Anyways, we could plug some more in, but this is what you're going to see. You're going to see it getting closer and closer to that slant asymptote. And then over here, if you plug in negative 1, I get 3. Negative 1, 3. I could plug in negative 3, and I think I get, was that negative 5/3? Anyways, we could plug in some other points, but you're going to see the over there as well. So see how as x increases or decreases in magnitude, see how it gets closer and closer to that green line as x shoots out to the right or as x shoots out to the left. That's that oblique asymptote. And finally, that brings us to our last example here. We've got 3x squared minus 10x minus 8. We'll go ahead and factor that first. 3x and x. At the bottom, I got difference of squares. So I got 3x. So let's see, that's 4 and minus 4. So notice I have two factors that cancel. See that those x minus 4s? So I'm going to make a little note here. This behaves, the original function right here, behaves like the simplified form, except it has a hole. It has a hole. Where does it have a hole? At 4. Okay, so except it has a hole at 4. So it behaves just like 3x plus 2 over x plus 4, except it's got a hole at 4. So let's go ahead and find our x-intercept by letting y be 0. So I got negative 2/3, 0. Let's find our y-intercept by letting x be 0. So I got a half, 0 comma half. So I got negative 2/3, 0. I got 0 comma a half. Our vertical asymptote, where do I have a vertical asymptote? At negative 4. Oops. Negative 4. Horizontal asymptote, you can go ahead and you can go back to that original function. We got 3x squared minus 10x minus 8 over x squared minus 16, or the simplified one, doesn't matter. Degree of the top is the same as the bottom. So you go ahead and take the leading coefficients. So 3 over 1. So 3 over 1. And then I'm also going to find where this hole is. That's going to be when I'm graphing this. at 4. Again, that came from, remember, x minus 4 canceled, right? So I had a hole at 4. Right? I have a hole at 4. I have a vertical asymptote at -4. This is my vertical asymptote. It'd be nice. Throw those in as well. Just as many as you need to throw in. Of course, we already have the intercepts also. But let's find where the hole is. Well, this is my simplified form. 3x plus 2 over x plus 4. Let's throw this in, the 4 value in, because this graph looks exactly the same, except this one, the simplified form, has no hole, so it'll tell me where the hole is. So I got 14 over 8, which is 7/4. So 1 and 3/4. So 4, 7/4. 1, 2, 3, 4, 1 and 3/4. So I got a hole right there. And I could graph a bunch of points, you guys, but this is what you're going to kind of see. It's just got this, got that hole right there. And I'd throw in some other points, like, let's at least throw in -5. 3 times -5 plus 2 over -5 plus 4. I got -13 over -1. So I got +13. So -5 is like way up here, +13. And I could plug some other points in, but this is kind of what you're going to see on that other side. So again, note the hole there. Note that hole, because those factors cancel. Well, thanks so much for watching and taking notes. We'll see you next time.